If a computer could try every path in a maze at once, would it solve everything instantly? That's the idea many people have about quantum computing. The truth is more interesting and more useful than the hype. Quantum computers really can explore vast possibilities in a way classical machines can't. But they only turn that ability into a big advantage when a problem has the right kind of hidden structure. Here's a plain English starting point. A quantum computer is a machine that calculates using the rules of quantum physics. Instead of bits that are either 0 or 1, it uses qubits, tiny physical systems that can be 0 and 1 at the same time. That blend is called superposition. And when qubits are linked or entangled, their outcomes are correlated in ways that classical logic can't mimic. The one big difference from the laptops and servers used every day is this: quantum computers exploit interference. Their computations behave like overlapping waves that can add or cancel. With the right setup, the waves that correspond to wrong answers cancel out, and the waves for right answers reinforce. So the simple version is, a quantum computer doesn't just try many possibilities in parallel. It sculpts that parallelism so the correct result stands out when measured. Why should this matter in practical terms? 2 reasons. First, there are problems that stump classical computers not because they're complicated to describe, but because too many possibilities exist to check one by one. Modern cryptography relies on that fact. If a method can cut through that explosion of possibilities with far fewer steps, some locks on today's data could be opened. Second, quantum systems are naturally good at simulating other quantum systems. Molecules, materials, chemical reactions, these are quantum by nature. A machine built on the same rules can model them more directly, offering new tools for drug discovery, clean energy materials, and catalysis. Picture the mental model that guides this entire topic. Think of a classical computer as a lone explorer in a massive maze. It takes a path, hits a dead end, backs up, tries again. It's fast at that, but still one path at a time. A quantum computer is like sending a swarm of ghostly explorers that can flow through many paths at once. Their trails overlap like ripples on water. Where paths lead to dead ends, the ripples cancel. Where paths converge on the exit, the ripples align and grow. When the swarm is photographed at the end, when the qubits are measured, the exit is more likely to be revealed. Let that sink in for a moment. The magic isn't that the swarm sees everything perfectly. It's that the maze is prepared in a way that makes the exit statistically jump out. Here's the idea to hang on to as the story deepens. Quantum advantage comes from 2 ingredients working together: a problem with the right mathematical pattern, and a way to encode that pattern into a quantum process that uses wave interference to zero in on answers. Without that structure, the ghostly swarm just becomes a blur. So how does this actually work under the hood, in approachable terms? Start with superposition. A handful of qubits can represent a huge number of possibilities at the same time. 2 qubits can hold a blend of 4 options. 10 qubits can represent 1,024 options. 20 qubits, about 1,000,000. This isn't storing every possibility as a separate file. It's holding one delicate overlapping state that contains all of them in different amplitudes. Think of them as strengths of the waves. That by itself doesn't solve anything. A camera pointed at waves sees only noise unless they interfere in a meaningful way. The computation's job is to choreograph that interference so the patterns reinforce the answers wanted. This is where problem structure enters. Many useful quantum algorithms rely on a puzzle hidden inside the problem, like a secret rhythm or a special mark. One famous example is periodicity, a repeating cycle buried in a function. Another is a marked item in a sea of unmarked ones. If that mark or rhythm can be applied to the waves without revealing the answer directly, it becomes possible to bend the interference toward the target. An intuitive way to say that: the algorithm taps the waves on just the right beats so that wrong paths go out of phase and cancel, while right paths step in time and get louder. What matters here is the choreography. The machine isn't reading every path, it's guiding a wave so the right destinations dominate when observed. Now a concrete taste of where this pays off. Cryptography first. Shor's algorithm is the poster child because it attacks the core of RSA encryption. RSA depends on the fact that multiplying 2 large prime numbers is easy, but undoing that multiplication, factoring the result back into primes, is classically hard. Shor turns factoring into a period-finding problem, and period finding has the kind of repeating structure that quantum interference can expose efficiently. That doesn't mean an overnight unlock of all secrets. It means that, with a fault-tolerant quantum computer at large scale, the math-protecting RSA and some elliptic curve systems would be vulnerable. That's why post-quantum cryptography, classical algorithms designed to resist quantum attacks, is being standardized now. Another widely cited result is Grover's algorithm. It speeds up searching an unstructured list. Think, find the one special entry in a giant phone book with no order. Classical search checks entries one by one. Grover's uses amplitude amplification, a kind of repeated wave boosting, to make the chance of landing on the marked item grow faster than random guessing. The speedup is quadratic, not exponential. That distinction matters. Quadratic can be meaningful for massive tasks, but it's not a silver bullet for every search or optimization problem. Then there's quantum simulation, the most natural fit of all. Chemistry, materials science, and certain physics problems involve many interacting quantum particles. Simulating those interactions exactly on classical computers becomes brutally hard as the system grows. Quantum computers represent those same states directly, so in principle, they can simulate much larger molecules with fewer resources. The promise here isn't a blanket acceleration of all science. It's targeted, new catalysts that lower energy costs, better electrolytes for batteries, more precise calculations of reaction pathways. Put differently, it's using physics to compute what physics does best. This raises a fair question. If quantum computers can explore many possibilities at once, why not speed up everything? The answer is subtle and surprisingly reassuring. Most everyday computations don't have the wave-friendly structure that these machines need. Sorting a database, rendering a web page, running most machine learning training, these are tasks where classical algorithms already exploit structure extremely well. There isn't a hidden rhythm to expose with interference. And where there is some quantum-inspired structure, for example in certain combinatorial optimizations, the known quantum gains are modest or problem-dependent. The deeper reason comes from complexity theory, the math of how hard problems are. The set of problems efficiently solvable by quantum computers is called BQP. It includes things like factoring, period finding, and many simulation tasks. It probably does not include notorious NP-complete problems like the general traveling salesperson, at least not in a way that makes them easy across the board. No proof settles this decisively, but decades of research point that way. The key idea is that quantum mechanics doesn't magically erase combinatorial explosion. It helps when the explosion has internal patterns quantum waves can exploit. So let's slow that down for a second. A quantum computer is not a universal speed machine. It is a specialist that crushes certain structures. When the structure lines up, periodicity, marked states, quantum interactions, the machine can leap. When it doesn't, classical approaches remain the workhorse. Now, how does a quantum algorithm actually steer those waves? A high-level walkthrough, without drowning in notation, is enough to build an intuition. It begins by preparing qubits in a balanced superposition. Think of it as laying down a faint ripple for every possible candidate solution at once. With n qubits, there are 2 to the n such ripples overlapping. That's the parallel canvas. Next comes a problem-specific operation sometimes called an oracle. Despite the dramatic name, it's just a reversible way to mark the good solutions without revealing them directly. In wave terms, it flips the phase of the marked ripples, like turning peaks into troughs for the winning paths. That flip is invisible in a still photo. It only shows up when waves collide. Now the choreography matters. A carefully designed set of operations causes the ripples to interfere. Where the phase was flipped, interference pushes amplitudes upward. Where it wasn't, amplitudes shrink. In Grover's method, this is repeated a number of times that grows roughly with the square root of the search space size, each pass making the marked answer more likely. In Shor's method, a different interference pattern, the quantum Fourier transform, extracts the hidden period all at once, revealing a clue that classical post-processing turns into factors. Finally, the qubits are measured. The giant wave collapses to a single outcome, a string of bits. If the amplitudes were sculpted correctly, that outcome gives the answer with high probability. Some algorithms repeat this whole dance a few times to drive the success rate even higher. What matters here is the role of measurement. The machine never reads all the paths. It reads one sample pulled from a wave that has been tuned to favor good samples. That's why structure is everything. Without it, tuning is random. With it, tuning becomes a shortcut. There's quiet elegance in that idea. Watching 2 ripples cancel down to a glassy surface or a line into a tall crest communicates more than pages of math. Quantum algorithms bottle that phenomenon at scale. Now ground that elegance in engineering reality. Today's devices are in the NISQ era, Noisy intermediate-scale quantum. They have tens to a few hundred qubits, and each qubit is imperfect. Errors creep in because the quantum states are fragile. They decohere, losing their delicate phase relationships in microseconds to milliseconds. Being too slow means the wave fades. Being too fast means control pulses aren't precise. That's why public demos today focus on toy problems and benchmarks with careful error mitigation. Escaping that noise requires quantum error correction. The concept is simple to say and hard to do. Use many physical qubits to encode one logical qubit, whose errors can be detected and corrected on the fly. The overhead is large, often hundreds or thousands of physical qubits per logical qubit for real-world error rates. A fault-tolerant quantum computer powerful enough to run long, deep algorithms will likely need millions of physical qubits, plus a blizzard of real-time classical processing to steer the corrections. That hurdle doesn't make the field impractical, it frames the timeline. In the near term, the most pragmatic path is hybrid. Classical computers shoulder the bulk of the workload, while small quantum processors tackle very specific subproblems where their wave mechanics offers a clear edge. For example, a classical optimizer might loop, calling a quantum routine to evaluate a tricky energy landscape in a molecule, or a classical cryptanalysis pipeline might test a candidate that a quantum step produces. So how should engineers and decision-makers reason about quantum's actual impact? A few simple heuristics go a long way. Ask whether the problem naturally has quantum structure. Hidden periodicities, interference-friendly marks, or genuine quantum dynamics are green flags. Factoring large numbers fits, simulating molecules fits even better. Searching a neatly indexed database does not. Sorting data does not. Most web services, analytics pipelines, and standard machine learning training don't present the right patterns. Another useful mental shortcut. Expect quadratic speedups for broad unstructured search and certain optimization heuristics, and expect exponential savings only in special cases like factoring and some forms of simulation. That sets realistic expectations. A quadratic gain on a trillion-item search can still be valuable, but it doesn't turn computing on its head. A genuine exponential gap, on the other hand, is transformative for the specific tasks it hits. One more angle is timing. For the next several years, quantum hardware will likely remain limited by noise and scale. That makes hybrid approaches, small problem instances, and domain-specific demos the responsible way to explore. Looking further out, fault-tolerant machines could make Shor's attack on RSA practical and open new frontiers in computational chemistry. The long run is compelling. The near term rewards clear thinking and targeted bets. Along the way, a few widespread misconceptions are worth clearing up briefly. The first is that quantum computers make everything exponentially faster. That's not the case. Shor's delivers an exponential advantage for factoring because factoring hides the right pattern. Grover's gives a quadratic boost for unstructured search. Many problems get no known advantage at all. The second misconception is that the technology is ready for everyday business workloads. Today's devices are remarkable prototypes, not production accelerators. There are impressive research wins and playgrounds for learning, but error rates and scale keep most applications on the classical side for now. A third misconception is that quantum breaks all encryption. It doesn't. It threatens RSA and some elliptic curve systems. Symmetric encryption like AES is less affected. It loses about half its strength under Grover's speedup, which can be restored by doubling key sizes. New post-quantum cryptographic schemes are being standardized to replace vulnerable ones before hardware catches up. There's something quietly inspiring about the engineering pushing this forward. Qubits can be trapped ions hovered over by lasers, or superconducting loops cooled near absolute zero, or defects in diamonds tickled by microwaves. Each platform is a bet on controlling nature at its most delicate. When it works, a whisper of physics becomes a calculation that no supercomputer could attempt directly. That's a special kind of progress, less flashy than headlines imply, more profound in what it reveals about information and matter. Tie the ideas back to the maze. The reason a swarm of ghostly explorers helps is that the maze itself has echoes. In problems like factoring, those echoes repeat with a rhythm that waves can latch onto. In simulation, the maze is physics, and the explorers are physics too, so the mapping is natural. In many everyday tasks, the maze is just walls with no music. Sending in ghosts does not find a tune that isn't there. What does that mean in practical planning? A smart way to engage is to align exploration with domains that promise structure, chemistry and materials, certain cryptographic analyses, specific combinatorial tasks with clear marks or symmetries. Pilot work should showcase a path to advantage that survives noise and scaling limits, not just a one-off demo. Teams can also prepare by adopting post-quantum cryptography as standards mature, and by building intuition with small-scale experiments that demystify the tools. There's also an educational payoff. Learning the mental model, superposition as overlapping possibilities, interference as the sculpting tool, measurement as the way to pull out one answer, changes how problems are seen. It's a shift from thinking, try everything faster, to shape a wave so good answers are favored. That reframing alone can highlight when quantum is a candidate and when it isn't. To round this out, take a brief look at a simplified factoring story without drowning in detail. Imagine a large number built by multiplying two primes. The quantum trick is to pick a random helper number and look at how its powers repeat when reduced modulo that large number. There's a cycle, a period, hidden there. A quantum circuit can set up a superposition over many exponents, compute those powers in parallel, and then apply a quantum version of a Fourier transform to pull out the period through interference. That period becomes a clue that classical math turns into the original prime factors. It's a chain, superposition to explore, a phase marking to encode the hidden pattern, interference to extract the rhythm, and a classical finish to get the factors. The feat isn't that every option was checked, it's that the wave was tuned to resonate with the cycle. By contrast, consider a task like sorting a list. Classical algorithms already minimize comparisons using structure in the ordering. There isn't a comparable hidden phase pattern that lets a quantum wave cancel wrong orderings and amplify the perfect one beyond what classical asymptotics already achieve. That's why not every task is a candidate. What about AI? Quantum machine learning gets a lot of attention. There are niche algorithms where quantum linear algebra might help, and research into quantum kernels and feature maps for classification is lively. For training today's large neural networks, the data access patterns, the stochastic gradients, and the well-honed GPU stacks leave little room for a general quantum boost. Specific subroutines may benefit, but a broad acceleration isn't on the near-term menu. So the story, when stripped down, is clean. Quantum computing is a new kind of calculator that leverages wave behavior to favor good answers in problems with the right structure. It isn't a faster laptop. It's a physics-native coprocessor that, for the right questions, changes the scale of what's tractable. Before closing, a moment of appreciation. The control required to keep qubits coherent long enough to do anything is extraordinary. Ultra-cold refrigerators cool devices to a fraction of a degree above absolute zero. Microwave pulses are timed to billionths of a second. Ambient vibrations, stray photons, even cosmic rays are potential spoilers. Yet, in that fragile dance, useful calculations have been performed that push the limits of verification. It's a quiet testament to how far both physics and engineering have come. Put all of this together into a way to think going forward. When a problem presents a hidden cadence, quantum can listen and sing along. When the landscape itself is quantum, quantum can model it directly. When neither condition holds, classical methods continue to dominate. Strategic value comes from matching problems to the tool that reflects their structure, not from assuming a universal speedup. So, how do quantum computers work, and what are they actually good for? They work by preparing overlapping possibilities, tagging the ones that matter in a way only waves can see, and orchestrating interference so that a measurement reveals a useful answer with high probability. They're good for problems with the kind of structure that waves can exploit, especially period finding and quantum simulation, and not broadly useful for everyday workloads that lack that structure. That's both limiting and liberating. It narrows the hype and it sharpens the promise. If this helped, a like and subscribe helps make more videos like this.